demo presents the deep learning component of the requirements collector tool. The deep learning component, as its name says, uses deep learning to classify requirements. Currently, the classification identifies between functional and non-functional requirements. It also labels requirements which do not contain information related to functional or non-functional requirements. In our GitHub repository, you will find a README file describing the context in which the deep learning classifier has been developed. It is part of our requirements collector tool, which supports, among other things, the automatic classification of requirements spoken during requirements elicitation sessions, as it is described here in this yellow region. It describes how to get started with the deep learning component and also the different system requirements that are necessary in order to run this code. Further references to previous research done related to the tool are listed at the end of our GitHub page. To start, the first thing that needs to be done is to ensure that Java 13 is installed in the computer, that at least 8 cores are available for execution, and memory RAM of at least 5 GB are available. The code can be, of course, cloned or downloaded from our GitHub repository. Once the code has been cloned or downloaded, please open the code in your favorite IDE. In this case, we use Eclipse. Our deep learning classifier works based on terns. A tern is an established unit of analysis in natural language processing as opposed to using single sentences. It describes when a person speaks in a conversation in between other speakers. Our deep learning classifier uses terns as well. In order to represent those terms in a learnable format, we use the word embedding provided by the globe vectors. Global vectors for word representation. Here words would be represented as multidimensional real value vectors. Trivially speaking, in a three-dimensional space, similar words lie closer together than those that semantically differ. Different pre-trained word embedding models are available. The available representation dimensions depend on the vectors, but range from 50 to 300. They also differ in terms of topic and number of tokens. For our initial development process and this prototype, we use the smallest set, the Wikipedia 2014 plus gigawords, which consists of 6 billion tokens and a representation of 50 dimensions. Here we have, for example, in this text, which is also attached to the code, one for 100 dimensions as well. So here we could use either from 50, in a range from 50 to 300. In our current implementation, we have one for 100 dimensions. A caveat with our deep learning approach is that the input size is depending on the number of words in a tern. Our approach here is to either pair terns with 0 values that are shorter than a certain threshold or cut them off. If they are longer, the number of inputs of our model is then the product of the fixated numbers of words and the dimension of the words representations. For the implementation, we use the deep learning for Java API, which you can see in the imported libraries for the project. It is an open source deep learning library, which could also run in a distributed environment. It has built-in support to read and pre-train word vector models and use them to look up the vector values for a specific word or a collection. Therefore, deep learning for Java relies heavily on the ND for Java library, which stands for n-dimensional arrays and linear algebra for Java. It is a scientific computing library which facilitates immensely the handling of multidimensional algebra. Before to start or before to run this code, it is important to note that the amount of gigabytes available for executing need to be established. In Eclipse, you can go to the properties of your project, then to the run and debug settings, and it is important to create the specification for this project. For this, You can then click in the button Edit, and here in the arguments, it is important to specify for the virtual machine the amount of gigabytes that it can use for execution. Once this has been done, we can execute this code. The model in this current state performs about as well as random guessing. This is because we do not have enough data available and could only work with a minimal training and validation set. In an initial test, we also use the smallest globe forward vector representation, as it has been explained. Here in the resources, you will find training set that has been used. Here you can find the different labels. So this is label data. Now it's because no requirement has been specified for this specific statement. And you will find also A and F classifiers, which also identify the different requirements. There is a test set, as is indicated here. We have a train set and a test set, which will be used for classification and training. The performance is expected to increase drastically if sufficient test data is available, as well as the representation vocabulary and dimensions are raised. Once it is executed, the program will also start to show all the different information and warnings regarding the requirements for executing this code. For example, here it indicates that at least it is necessary to have 4.9 gigabytes and the different libraries that we have used. This initially has been developed to be executed in Windows 10. It is important to highlight that for the correct execution, it is necessary to create an output folder. This is not created, or this has not been provided with the project that has been shared, but it is important that when creating the Eclipse project, this output folder is created as well. This project has been imported into Eclipse as a Maven project. For the reason, the POM XML file, you can see it here. When importing this project, it is important to select or to indicate to your IDE that it is a Maven project. Here now see that after some seconds that the execution started, and now the train model started to classify the requirements. As you can see here, the current precision is of 33%, and it has been classified the requirements in different options. So currently our model differentiates between three labels, which are here represented as 0, 1, and 2. 0 means for none, so non-functional or functional requirements have been identified. Non-functional is labeled with 1, and functional is labeled with 2. A caveat of this deep learning approach that it only cares indirectly for the fact that terms can be both labeled 1 and 2. A turn that falls into both categories would have probabilities around 50% for both labels, which can be interpreted individually, but is not represented in the standard evaluation method of machine learning classifiers. This code in its current version will continue executing the training set and the test set endlessly in order to try to adjust the precision and the accuracy levels. So the model is pre-trained all the time using exactly the same training set and test set. It is expected that with new training set and test sets, this algorithm will grow and relearn in order to classify much better functional and non-functional requirements.